and drainage. Yeah, so we looked at groundwater, and now an extension. By extension, we know that anytime groundwater intersects the surface, then we are going to have a stream. So our focus today is starting from streams and drainage. What's a stream? It's just a body of water that carries rock particles and dissolved ions and flows downslope along a clearly defined path. And this path we call a channel. So a stream has different names, and some of this depends on where you are. It's in some places it's called a branch, or a brook, or a beck, or a creek, river. So from here we can see that a river is nothing but a big stream, right? So streams may vary in width from a few centimeters to several kilometers. And we do know that the biological habitats just around the area of a stream, we call that the riparian zone. Riparian zone. And streams, there are some streams that flow from year to year. So they are always there. Dry season, wet season, from time to time, the stream is there. So those are called perennial streams. Then we have some other streams that they appear and for a period, maybe during the wet season, and then in the dry season, they dry up. So they are intermittent streams. And then we have those that only appear maybe when there is a rain or just in a short while and vanish. So these are ephemeral streams. So those are the three categories. So here we have a main stream. We have the drainage divide. All right, drainage divide. So this more or less encapsulates this entire system of this particular stream and its tributaries. We have the various tributary streams, and this is the main stream. All right, and the space, the area in between is the interfluent. And then ultimately the stream is going to have a mouth. All right. So the extent of land basin drained by a stream is termed its drainage basin. Its drainage basin. And so in British English, that could be called as a watershed, or in the US as watershed, and in British as a catchment. And so when we talk about a basin, then that's going to compose of smaller basins. All right. What's the importance of streams? We do know that streams are important in the water cycle. All right, they serve as conduits in the water cycle. They are very important in recharging our groundwater regime. Then streams also act as the main medium for transporting sediments and particles, rock fragments, in the production of sedimentary rocks. They do carry lots of dissolved ions, the products of chemical weathering into the ocean. And then also streams are very important in weathering, erosion, and mass wasting processes. As far as we are concerned, to both humans and animals, streams may also serve as major sources of drinking water, and then may also be able to transport us from one place to the other, both goods and people. All right, so here we can think about the major rivers like the Volta River we have. We have a lot of transportation on it. And they also serve as a corridors for fish and wildlife migration. When we talk about a stream channel, we know that is the conduit for water being carried by the stream. And the stream can continually adjust its channel and the channel shape and path depending on as the amount of water passes through. So depending on the volume of water that is passing through the channel, the stream is going to attempt to adjust the shape and then the path. So we do know, for instance, over here, we see that we have this particular direct channel precipitation. Then we can have the stream also being recharged more or less by the water table as the water table intersects, by groundwater regime as the water table intersects the channel. Overland flow as well can recharge the stream. And then in between that, we can also have interflow to recharge the stream. So these are the main sources. And we already looked at discharge, right? And discharge is the volume of water passing any points in the stream. So you remembered when we looked at the Darcy's principle, we looked at discharge. All right, discharge. Discharge of a stream is the volume of water passing any point on a stream at any point in time, and the unit is volume per time, right? Volume per time. So then we can now look at the cross-sectional shape. So the cross-sectional shape is going to vary with position in the stream and then discharge. And the deepest part of the channel occurs where the stream velocity is the highest. So we can look at the cross-sectional shape. And this is going to vary with the position in the stream and then with the discharge. So the velocity is always highest where the deepest part of the stream is. All right, that is where we have the highest velocity. And both the width and then the depth increases downstream because discharge is going to increase downstream. All right. And as discharge is increasing, then the shape is also going to change with the stream becoming deeper and wider. So basically, that's what we are talking about. So in this direction, we have increasing discharge. That is the amount of water that is passing through at any point in time. All right. So at a particular point, the amount of water passing that point is the discharge, right? That's the discharge. So when the stream is small, so we see right here. So this is the entire channel width. All right. In terms of cross section, so the discharge is going to be the cross-sectional area. That is this area here times the velocity of the stream, the velocity of the water times the cross-sectional area. And then as we move downstream, what is happening? The stream is getting bigger and bigger. It's getting wider and wider, right? So as it gets wider, correspondingly, it adjusts the depth also. So it gets deeper. And then as we go on and on, we see that the width increases significantly and correspondingly the depth also increases. And that is why we are saying that both the width and the depth increase downstream because discharge increases downstream. So as the stream develops and moves from source all the way downstream, from upstream to downstream, we see the width increasing and the depth also increasing. As such, the discharge will also increase. And we explain that the discharge is nothing but the cross-sectional area times the velocity. We could look at streams in terms of long profiles and then base profiles. Long profiles and then base profiles. So in terms of the long profile, we get that by plotting elevation against the distance of travel. So elevation of the stream against the distance of travel, that is the long profile. And we see that from the source where the stream starts from, the gradient is very steep. And so as it moves down, then the gradient reduces as the channel continues to widen and the cross-sectional area widens, right? The gradient reduces as it moves downstream. So that is what we call the long profile. A plot of elevation versus distance. And this usually shows a steep gradient near the source of the stream and a gentle gradient as the stream gets to the mouth. So here we see the long profile from the source, very steep, and then as it gets to where it discharges, or the mouth where it empties into a bigger water body or the sea, then we see that it becomes more and more gentle, and it's now meanders and meanders, right? The second thing we want to now look at is the base level, and this is defined as the limiting level below which a stream cannot erode its channel. That is the base level. The limiting level below which a stream cannot erode its channel. So when we have streams that empty into the oceans, then the base level is the sea level. So at the sea level, they cannot erode their channel again. All right. They cannot erode the channel again. And at that point, that's the base level. We could also have local base levels if the stream runs into a problem, like meets a body, for instance, a resistant material, like a body of rock. Or maybe we have a dam and the dam impedes the further channel erosion, or where the stream finds its way into a lake, then that would be a base level. So here we see the original long profile, which is the plot of elevation against distance, right? And then this is the long profile. And then as we get downstream, we know the gradient should become gentle, but in here we have a dam, right? Because of this dam, then we have a new local base level because the stream will not be able to erode the channel around here. And then as we go beyond the dam, then we have the general regional base level, where the stream cannot erode its channel any longer. So that is the concept of long profile and base level. With long profile, we are plotting elevation against distance. And then we see that at the source, it is very steep, that's the gradient, and downstream is very gentle in terms of gradient. And this is typically closer to the mouth of the river, where it empties into the stream, into a sea or a bigger water body. Then the base level, we are defining that limiting level below which the stream cannot no longer erode its channel. All right, so yeah, this could be the sea level. So at this level, for instance, the delta zone here is the base level because there's no more erosion of the channel width. It just comes gradually, meanders and empties itself into the sea. So this is the base level. And then we can have a local base level where maybe we have a dam and then the regional base level. Then a stream's velocity is going to depend on the position in the channel. And then also irregularities in the stream channel caused by resistance rock and then the gradients of the stream. So the time it takes a given particle of water to move from a point to another point is what we call the velocity of the stream. The time it takes a given particle of water to move from one point to another or to travel a given distance is what we call the velocity of the stream. And the flow, the nature of flow can be laminar or turbulent. So streams either flow in a laminar path or turbulent nature. And when we talk about laminar, it means that we have a very gentle flow. So all the molecules are traveling along similar parallel path, very gentle. Like when you just stand before a big water body like a river, you see it's very gentle. It's as if it's not even moving. So that is laminar flow. Then we could also deal with turbulent flow. All right. So in the case of turbulent flow, we have this kind of flow pattern that is not regular. All right. So each particle is taking an irregular path. And this we can typically have, maybe imagine we have heavy rainfall and you see water moving through a gutter. And that type of flow and carrying particles, that kind of flow is turbulent flow. And the average linear velocity is generally greater in laminar flow than in turbulent flows. This charge, as we already mentioned, is the amount of water passing any point at a given time. And this charge is equal to area times the velocity. All right, the cross-sectional area times the velocity. And the cross-sectional area is the width, the channel width times the depth, the width times the depth. So length by breadth, all right, length by the depth, the deepness of the river. That gives us the area. And then we multiply that by the average velocity, and that gives us the charge. And as the amount of water in the stream increases, the stream needs to adjust its velocity and cross-sectional area in order to form a balance. So for instance, we know that this charge is going to increase as more water is added through rainfall or other streams, groundwater seeping into the stream and all that. This charge will increase, or the amount of water flowing through the stream will increase. So for that reason, then the stream has to adjust. And it adjusts by increasing as discharge increases, then the width is going to increase. The deepness of the water, the stream, will also increase. Then the speed of flow of the water will also increase. All right, the average velocity of the stream increases. And then what happens to the gradients? We know that when the width increases like that, the gradients will reduce. So the width of the river or the stream will increase. The deepness or the depth will increase. The velocity, the speed of the stream will increase. The water in the stream increases. But the gradients will reduce. Right. Then we can now talk about the stream loads. Stream loads. In terms of stream loads, we can mention it refers to the particles, the rock particles and dissolved ions carried by the stream. These are called the stream's load. The stream's load. All right, the stream's load. So the stream's load is divided into three parts. And the first part is what we call the suspended load. So these are particles that are carried along with the water in the main part of the stream. So that is the suspended. So it is carrying it. The stream is carrying the particles. So the particles are suspended in the stream. So that is the suspended load. And the size of these particles are going to depend on the density. All right, the weight, the density and the velocity of the stream. So it's going to depend on their density. That's the density of the particles, like the weight of the particles. All right, the density, the mass, the weight divided by the volume. So the density of the particles, that's the heaviness of the particles, and the velocity of the stream. So higher velocity currents in the stream will carry larger and denser particles or heavier particles. If the stream is traveling at a very high speed, then more particles can be carried. The second type of load is called the bed load. Bed load. So these bed loads, they are coarser and heavier particles, and they remain at the bottom of the stream or the river most of the time. But they can move by a process called saltation, which is just like jumping. All right, so like a particle moves, it jumps, and then because it clashes with the other particles in the stream. So that is called saltation. Saltation, the process by which a particle that is on the bed of the stream, on the very floor, bottom of the stream, moves by jumping. That is saltation. And this is as a result of collision between the individual particles, and then turbulent eddy currents. Eddy currents. All right. Then we could also look at dissolved load. Dissolved load. So these ones may not be visible to the eye. So these are the ions that are introduced into the water by chemical weathering of rocks. So for the dissolved loads, we do not see them with our eyes. The bed loads, they are heavier particles and coarser at the bottom of the stream. And then we can also talk about the suspended loads, which are carried in the main channel of the stream. So that is the suspended load. Suspended load. Now we want to talk about floods and floodplains. Floods occur when the discharge of the stream becomes too high to be accommodated in the normal stream channel. So when the discharge becomes too high, we know that what happens? We know that the channel width is going to increase, or the stream will widen its channel by overtopping the banks. And once that happens, then the low-lying areas in the catchment area of the stream will experience flooding. And the areas that become flooded, we call those ones the flood plains. Flood plains. So here we have flood plains, and this is normal conditions. But when the discharge increases, due to maybe heavy rain and all that, then we are going to have flooding. And the area that gets flooded is the floodplain. All right, so here we see various floodplains. Floodplains. Then we can also look at channel patterns. So we have straight channels, and we do know that straight channels are not common. Streams are likely going to meander. That's the bending nature. The snake behavior is meandering. So streams are likely going to meander. So when they do occur, when the straight channels do occur, it's usually controlled by a linear zone of weakness in the underlying rock, like maybe a fault or joint system. And even in a straight channel segment, water is going to flow in a sinuous fashion. All right, we see this bend, sinuous fashion. All right, so you remember we talked about the highest velocity streams. So we are going to have this kind of cross-sectional area, then medium velocity, then low velocity. We are having a very wide width at low velocity, but the highest velocity will be at the bottom section. All right. So this is a example of straight channel. Then the usual one we know is the meandering channel. Meandering. All right, meandering. This kind of S-shaped meandering. Because of the stream's velocity structure, low gradients flow, straight channels will eventually erode into meandering channels. And erosion will take place on the outer parts of the meander. So at the outer parts, we are going to have erosion, and then the position will occur along the inner part. So erosion at the outer part, deposition in the inner part. All right, erosion in the outer part, deposition in the inner part. So sediment deposition will occur along the inner meander bends because the velocity is highest at the outer and then lower in the inner side. Because from here, the stream will hit here at a high velocity, and this side will have a lower velocity. So deposition is around here. And such deposition of sediment results in exposed bars called point bars. Point bars. So around this zone, we can have point bars. Point bars. So when this continues and continues, all right, then over time, what is going to happen? We keep on having deposition around the zones where the inner parts of the stream. Then with time, we are going to have all this entire area cut off. And when that happens, we form what you call an oxbow lake. Oxbow lake. All right, oxbow lake, where sediment deposition in the inner part becomes so much such that that particular part is chopped off, cut off, and then the stream more or less just continues its channel and leaves behind that small lake, that lake, and we call that an oxbow lake. Then we can have braided channel. So for streams having highly variable discharge and easily eroded banks, sediments are going to get deposited to form bars and islands in the middle, right in the middle of the channels during periods of low discharge. So in such a stream, the water is going to flow in a braided pattern around the island. So in the middle here, we have sand. Here's sand, here's sand, here's sand. Then the water is flowing around it with low velocity, flowing around the channel. So we call this type of channel a braided channel. But when we have, this could, for instance, happen maybe in the dry season, right? But when we have periods of high rainfall, then all these sediments are going to be eroded. Then when discharge reduces, these islands will return again. All right, so that is the nature of the braided channels. And we have island bars in the middle, islands and bars in the middle. All right, so now on to erosion by streams. Streams, we do know, do a lot of erosion because they pick up rock fragments and transport them to new locations. And the size of these fragments that can be transported is going to depend on the speed of the stream and whether the flow is in straight path, gentle path, laminar, or turbulence. Turbulence. If the flow is turbulent, then it means that fragments are going to stay suspended for longer compared to if it is a laminar flow. And then we also know that streams can erode by undercutting their banks. So from mass wisdom, we learned about undercutting, where they eat below the level and then the top part will collapse into the stream channel again. So that is undercutting. So streams can erode by undercutting their banks. And a sudden change in the speed of the stream can also result in deposition by the stream. So within the stream, the velocity also varies with position. And so if the sediment gets moved to the lower velocity part of the stream, like we said, the outer part, we have high velocity, inner part, lower part, then the sediment will come out of suspension and be deposited, just as we saw in the formation of the Oxbow Lake. Now we know that as a stream overtops its banks during a flood, the velocity of the flood will first be very high, but then it will suddenly reduce as the water flows out over the gentle gradients of the floodplain. So because of the sudden reduction in this velocity, we are going to have some deposition of sediments. And this will eventually build what we call a natural stop or levee. So this is the initial stream. No flooding has occurred yet. After flooding occurs, the water is going to flow gently, so the speed has reduced. So the sediment it was carrying is going to deposit at the banks. So this deposition is called a levee, which is like a natural stop. So before we can have another flood, the channel the water level needs to rise far higher than the original water level that was able to cause the flooding because of the natural levee that was there. So with each subsequent flooding, we are going to have higher and higher levees. This is a levee, and this is a levee. All right, levee. Then we can also talk about alluvial fans and then river deltas. All right, so let's say we are dealing with a mountainous area. An alluvial fan or cone-shaped deposits of sediments. They are just cone-shaped. It's a fan or cone-shaped deposits of sediments that is crossed and built up by streams. So in this area, we have a mountainous area, a mountainous stream, a high elevation. Then as we come to lower elevations, we are forming this kind of distributary channels, not tributary, but distributary. So this area is flat, right? So the river patterns, it gets to a flat area, then it's divided into tiny branches. And then this whole area, this is the alluvial fan. So this is distributary. They are distributary channels. All right. So distributary channels are coming from a single point. That is the source at the top, the apex of the fan, and over time begin to occupy many positions. That's the distributary channel. And we can talk about the river delta. So the delta is it's formed at the mouth of a river. So we know that the mouth is where the river flows into a bigger river, a bigger lake, an ocean, the sea, and all that. And deltas are formed from the deposition of the sediments carried by the river as the flow leaves the mouth of the river. So we know that the lowest velocity occurs around here. Here we do know that the river can no longer erode banks, that's the base level. And at this point, we have deposition to form the delta. The delta. This is formed, these deltas are formed at the mouth of the river, but these alluvial fans occur just as we leave a mountainous area to flatter areas. So that's the difference between the two.